Hi everybody. This time, make sure you grab yourself a nice light latte. Milky. Okay, so let's get a decent pen. So we're going to have a crack at 3.4. This is the first example of a composite problem where we've got steel and two brass sections either side. For simple problems like this, how we're going to examine it is by imagining that we're not bending a composite material, but we're going to bend something roughly equivalent. Now all the way through we have brass, all the way through we have steel. So what I'm going to do is I'm going to pretend that this problem is going to become something like this problem, where we've got brass all the way through. Okay, so when I'm bending a composite material, I don't really have any things to bend around here, but so let's say I'm bending my DVD here. So imagine this is made out of composite material, and imagine this inner section here is stiffer material. So when I bend this, what's going to have higher stress? It's going to be the thing in the middle, if that's got a higher Young's modulus. So stiffer material means higher Young's modulus means higher stress. So what I can do is, let's say this stiff inlay, and then I'm going to pretend that the outer less stiff material is the thing I'm now going to try and bend. So I'm now trying to bend all of that. That's the basic concept that we're trying to achieve. So this is equivalent to my two chunks of brass and my steel. Okay, in actual fact this ratio is different. It's only going to be a 2-to-1 ratio. So this distance here is actually two of these. It's a badly drawn diagram. Okay. Right, so this is steel, and here everywhere is brass. So trying to bend this thing here with two brass sections and a middle steel section is the same as trying to bend these two brass sections, and then if we double the area and fill it full of brass, that will be the same as trying to bend the steel. That's the basic concept. Determine the maximum stress in the steel and the brass when it is being bent by a moment of something or other. The very first thing you do for these composite problems is you find something called the N factor, and the N factor is the ratio of the Young's modulus. Typically you use the lower Young's modulus is going to be the thing that's going to be the imaginary replacement of the actual thing that you're bending. So this is the Young's modulus of the brass, and here we've got the Young's modulus of the steel. So that's 200 divided by 100, so you've got an N factor of 2. So this area here needs to be twice this area here. Okay, doesn't look it, I'm afraid. Badly drawn diagram. Right, so trying to bend this problem, well, that's straightforward, isn't it? All I need is to know what the second moment of area is. So I'm going to use BD to the power of 3 divided by 12. To make this area twice this area, I need to keep the height the same, because as I'm looking for the stress profile going through, the stress profile has to stop at the start, stop at the same position here and here. So the height's the same, so the only way to double the area is to make it twice as wide. So this area here on the still diagram is 20 millimeters. That means that this thing here is going to become 40 millimeters. Okay, so we've got 40 millimeters. Then we've got 10 millimeters for these sections. Okie dokie. They have a depth of 80 millimeters. So the overall, this width of the imaginary thing that I'm trying to bend is going to be 60 millimeters multiplied by the depth of 80 millimeters to the power of 3 divided by 12. So my I is going to be 60 times by 80 to the power of 3 divided by 12. So that's 2.56 times 10 to the 6 millimeters to the power of 4. Okay, that looks straightforward. Now let's grab the engineer's bending equation. I'm only going to want the first two bits. Whoops, stress over y. Oh, everything's going wrong. So therefore I'm looking for stress m over y over I. What next? What next do I want to do? So the distance to the top and the bottom from the neutral axis is still going to be this location here. So that's going to be 40 millimeters. M, given in the question as 5,000 Newton meters. Let's convert things to SI units. So 5,000 times by 40 times by 10 to the minus 3. Let's convert this into meters to the power of 4, so that 10 to the 6 becomes minus 10 to the minus 6. So that gives me the stress top and bottom, and that gives me the stress for this thing here, which is brass. So I get a stress of 78.13 megapascals. Now we've got to imagine we're now going to go back to the original thing that we're trying to bend. So the stress in the brass sections is going to have a maximum stress. Let's assume this is being compressed at the top, stretched at the bottom. So maximum compressive stress of minus 78 megapascals at the top, plus 78 megapascals at the bottom. But what about this section here? Well, to get it back to this problem, I'm going to have to squeeze it back to the original area, so halve it, which means that the stress is now going to go up twice. So the stress in this section is going to get squeezed, which means stress over area, reducing the area, the stress goes up. So the stress in the still section is going to be twice that, and again what we're going to be doing there is using the n factor. So equals n times by the stress in the brass section, which will be 2 times that. So that's 156.3 megapascals. Okay. Right, that's good enough for me. Let's stop there.